I'm sharing my screen. Yes, my screen is visible. Is it visible now?
Yes.
Okay. So today I will see about this MOS capacitor. Okay. MOS is nothing but what? MOS is nothing but it's a metal oxide semiconductor. Okay. So that means MOS capacitor consists of metal oxide and semiconductor layer structure. Okay. So it consists of metal oxide semiconductor. Without drain and source, we call as MOS capacitor. Okay. In the MOSFET, so without drain and source, if we call as MOS capacitor. Okay. It forms a voltage dependent capacitor. Okay, voltage dependent capacitor. Compared to BJT, it occupies less space. Okay. So that means we can say that the heart of any MOSFET or CMOS. Okay, CMOS is MOS capacitor. MOS capacitor. Okay. So if you see, so this is suitable for integrated circuits. Okay. MOS capacitor is not widely used in the device, but MOS capacitor present in all the MOS transistors. Okay. So whatever the MOS capacitor is there, that will be always present in the MOS transistor. Okay. This is about MOS capacitor. And so if you see the MOS capacitor, so you have like this is gate terminal. Okay, this is nothing but VG. Okay, and this one is metal, and this one is oxide, silicon dioxide, and P-type substrate. Okay, this is a lightly doped. This is lightly doped P-type material. P-type material. Okay, and this is substrate terminal. VB is substrate voltage. Okay, this is the substrate terminal. Okay, so mm, so metal or polysilicon material is used for metal layer. For metal layer, we can use metal. So mainly metal means we are using copper. Okay, we are using copper. Metal or polysilicon material is used for metal layer. SiO2 is acting as a dielectric. So that means MOS capacitor means here if you see this is one terminal and this is another terminal. Okay, this is another terminal. You are giving positive, here you are giving negative. Okay, so that means what you are doing here. So in between these two, there is a dielectric. Okay, this is dielectric. Okay, so this is nothing but SiO2, silicon dioxide. Okay, silicon dioxide. This is acting as a dielectric layer. Okay, the dielectric layer that forms a capacitor between gate and substrate. Okay, these are the two terminals. This is gate and this is substrate. Okay, this is substrate. Okay, so how much is the thickness? Thickness is the order of 10 nanometer to 50 nanometer. Okay, so in semiconductor, p-type and n-type semiconductors are used. Okay, capacitance of mass capacitance depends on the voltage applied in the gate terminal. How much of the capacitance? Okay, always this is connected to ground only. Okay, this is anyway this body voltage equal to 0 only. So the capacitance is depends on what which that means how much of voltage you are applying to the gate. That is a VG. Okay, capacitance depends on the voltage applied to the gate terminal. Usually, whatever our body is grounded. I told you, no. Okay, this body is nothing but grounded only. Okay, so when gate is applied, when gate voltage is applied, body is connected to ground only. Okay, so this is about structure of MOS capacitor. Okay, yeah. Any doubts in this? What is this MOS capacitor and structure of MOS capacitor? Shall I move forward?
Yes, sir. So,
Okay. Yeah. Next you see. So we already seen the energy band diagram of p-type substrate. No? So that means energy band diagram. So you have like energy band diagram. You have valence band and you have conduction band. And this is nothing but intrinsic Fermi energy level. Okay, intrinsic Fermi energy level. And for p-type semiconductor, what is the mu Fermi energy level? This is towards the valence band or towards conduction band? We already seen in semiconductor physics now.
Yes, sir.
Right?
Valence band.
Towards the valence band. Why? Because majority carriers are holes. So that means here Fermi level is towards the new Fermi level is nothing but towards the valence band. Okay. So here this means what is the what is the distance between this valence band and conduction band? If you take for silicon the distance is 1.1 electron volt. Okay, 1.1 electron volt, and this is nothing but nothing but free space. Okay, so free space band, the distance between conduction band and free space is nothing but the distance. This we can call as work function. Q into Zine, Q into Zine, that is equal to 4.15 electron volt. Okay. So how much of energy required to jump the electron from conduction band to free space? This is nothing but this much of energy is required. Okay. So we already seen like so for p-type semiconductor, Fermi potential is approximately this is the work function kT by q ln ni by na. For n-type semiconductor, the work function is kT by q ln nd by n. Okay, and q into Zine, this is nothing but what? Electron affinity. This is nothing but electron affinity. Okay, so this is the energy gap between what? Electron affinity, the energy gap between conduction band and free space. That is nothing but electron affinity. Okay, so the energy required to move the electron from Fermi level to free space. Okay, so my Fermi level to free space. So how you can find out? That means this distance, this distance. What is this distance? EC minus EF. This distance is nothing but EC minus EF plus this one, Q into Z. Okay, so this much of energy. So that means total energy. So total energy Q into phi s, Q into this distance. Okay, Q into phi s. I can write as what? This is Q into phi s. Okay, so Q into phi s equal to, I can write as this is equal to Q into sine plus EC minus EF. EC minus EF. Okay, so this is the energy required to move the electron from Fermi energy level to the free space. Okay, so this is free space. Okay, this is the work function. Okay, energy required Q into phi s. Okay, so this is the energy band diagram of p-type substrate with respect to what? Valence band, conduction band, and with respect to free space. Do you understood? Any doubt in this? Your response?
No,
Hello.
sir.
Okay. Next, energy band diagram of what? MOS capacitor. Okay. So MOS means what? MOS means metal oxide semiconductor. Okay. Metal oxide and semiconductor. Okay. So that means if you want to draw the energy band diagram for MOS capacitor, you need to draw the energy band diagram for metal as well as energy band diagram for oxide, and you need to draw the energy band diagram for semiconductor. So you take the metal, that is aluminum. Okay, this is the energy band diagram. Okay, so energy band diagram means what? In the different types of materials we have seen, and the distance between valence band and conduction band will overlap in the metals. Okay, there is carbon energy gap is very less. This is if you see that this is Fermi level. So Q into phi m. So what is the work function of Q, this one? 4.1 electron volt. Okay, this is for metal. Okay, this is for metal. Okay, energy band. And oxide, if you take, oxide is nothing but this is the insulator. This is nothing but insulator. We already seen for the insulators, energy band gap is more around 6 electron volt. We already seen no, during the semiconductor physics. we already seen. So it is difficult to move the electrons from valence band to conduction band. So energy gap is more. So energy gap is around 8 electron volts. And this is a Q into Xine. This is the energy required to move the electron from conduction band to free space. Okay. So this is the energy of electron required to move from Fermi level to free space. Okay. Next, this we already seen P-type material. This is nothing but P-type material. So P-type material, if you see, so this is the conduction band, this is the conduction band, and this is the valence band, and this is the intrinsic Fermi energy level. Okay, and as this is a P-type, majority carriers are nothing but holes. Okay, holes. So what happens? Fermi level will be towards valence band. Okay, and this distance is q into phi f. Okay, and this distance is q into phi s. Okay, we already seen this is equal to what q into sine plus ec minus ec minus ef. Ec minus ef. We already seen. Okay, ec minus ef. Okay, so we need to combine these. Metal, oxide, and semiconductor with one energy band diagram. Did you understand how I am doing? Here, if you want to calculate this one, q into phi s, total distance. So that means q into phi s equal to what? Q into sine. Okay, this is q into sine. This value plus what is Eg? Total energy gap is nothing but Eg. Okay, Eg. Here half of this means nothing but what? This half, how we'll get, this is nothing but Eg by 2. Okay, so this is equal to Eg by 2, half of the energy gap, plus this value is nothing but Q into phi f. Q into phi f. Okay, this is nothing but total work function, Q into phi s. Did you understood this energy band diagram? Shall I move forward?
Yes, sir.
So we are adding the energy band diagram of metal, oxide, and semiconductor. So pure metal, we are using aluminium. So energy gap means we already seen for metals. Okay, so there is no energy gap. Okay, both the conduction band and valence band will overlap. So we can say that Fermi energy level is. So this is the Fermi energy level, and this is the distance between Fermi energy level and free space. Okay, and if it is a oxide, Fermi energy level is more. Okay, and this is the distance between conduction band and oxide, and this we already see in the p-type material. Okay, the first itself I explained the energy band diagram of p-type substrate. P-type substrate, that p-type substrate, I mean, I just replaced here semiconductor. What about remaining? Shall I move forward?
Yes, sir.
Sir.
Okay, next you see. So energy band diagram of mass structure. So mass structure means, so when we combine three MOS materials, what are the MOS materials? Metal, oxide, and semiconductor. Okay, when you combine, okay, Fermi level, whatever the Fermi level is there, that must lined up in the single line. Okay, single line, and free space must continuous. Okay, free space must continuous. Okay, so that means here what I am doing in this, just I am combining this Fermi level, and here some Fermi level will be there for the oxide, and here this Fermi level, this Fermi level. Okay, this Fermi level I'm combining. I'm just combining. So what happens here? So total Fermi level. So this is total Fermi level. Okay, this is the total Fermi level. So what happens for the metal? So this is let us consider this is nothing but free space. Okay, this is the free space. This is the free space. Okay, so this is nothing but for metal. This is the free space. Okay, after that. what happens? Oxide. Oxide is there. Oxide means what? You will get a ramp function. You get a ramp function. Oxide. Okay. And E naught. So this one you are getting some tilt over here. You will get curve, and this is nothing but free space. This is the total free space. And here this will conduction band also shift, and you will get like this. This is the conduction band, and this is the intrinsic level. Okay, and this is nothing but valence band. Like this, if you combine metal, oxide, and semiconductor, you will get like this. You will get like this. Do you understood how I am combining this metal, oxide, semiconductor? Any doubt in this? Hello. Shall I move forward? Waiting for your
Yes, sir.
response. Hmm? So I'm making this free space as common. Okay, free space as common and combining all this Fermi level. Fermi level also common. Okay, so Fermi level common means here Fermi level is down. Okay, so you need to you need to make up one. Okay, so that's why you are getting like this. You are getting like this. Okay, so you are getting like this in the semiconductor. Whereas for oxide, you are getting a ramp function. This is the ramp function. Okay, and this is the metal with respect to what free space. And here you will get conduction band, and there is no conduction band and valence both will overlap. So here you have conduction band, intrinsic level, and valence band. Okay, is it fine now? Shall I move forward?
Yes, sir.
Okay, next you will see. So ideal MOSFET, ideal MOS cap means these are the assumptions. You need to consider work function of metal is equal to work function of semiconductor. Okay, oxide layer has no charges. Okay, oxide layer has infinite resistivity and no surface state or oxide semiconductors are there. Okay, this is ideal MOS cap. Okay, and next you will see. So this is a basic. Ideal MOS cap. So that means there is no telltale. This is practical. So these are the practical energy band diagram for practical MOS cap. Okay, MOS, metal oxide semiconductor capacitor, MOS capacitor. But ideal MOS means you will get a straight line over here. Okay, work function will be straight line, free space will be straight line, and conduction band, intrinsic Fermi level, and this Fermi energy level. These all will come in the straight line. Okay. So this is the energy band diagram for ideal MOS cap. Okay. Next. Yeah. 1 second. Okay. This is one example. Suppose if you take, suppose consider the MOS structure that consists of what P-type doped silicon substrate and SiO2 layer, a metal oxide, equilibrium Fermi potential of silicon. Q into 5p they given. Okay. Q into 5p equal to what? 0.2 electron volt. Using electron affinity of silicon and work function of aluminum given in figure, calculate the built-in potential difference between the MOS capacitor is asking. Okay. So that means from the figure he given Q into 5m. Okay. Q into 5m they given. Okay, and Q into Zine value also they given. Okay, and this is the energy band gap 1.1 electron volt, and this is the work function between the Fermi level and intrinsic Fermi level. Okay, so from this what I can do, he given the metal work function. What is the metal work function? 4.1. This is the metal work function. Metal work function. Okay, metal work function. And next, semiconductor work function, that means here Q into phi s. Q into phi s, how to calculate? I already told. Q into phi s, semiconductor work function equal to what? Equal to Q into Zine. Q into Zine. Okay, this value. This value. plus plus this is the total energy banding. I want to calculate half of this, so that means that this is the uh, this is uh, this is nothing but energy band gap Eg by 2. Okay, so that means plus Eg by 2, Eg by 2 plus Q into phi f. This is the total work function of my semiconductor. Okay, so that means Eg by 2. This is nothing but this distance plus this distance. Okay, this distance. Sorry, this distance. Okay, plus this distance plus this distance. You will get the work function of semiconductor. Okay, so here Q into sin 4.15 given, already given. Okay, Q into sin equal to 4.15. Okay, and Eg by 2 equal to how much? Here Eg equal to what? Eg equal to 1.1 electron volt. Okay, 1.1 electron volt means Eg by 2. What is Eg by 2? 0.55 electron volt. 0.55 electron volt. Okay, so this is 0.55, and Q into phi f is already given in the problem. This is nothing but Q into phi f, 0.2 electron volt. Okay, equilibrium Fermi potential Q into phi f equal to 0.2 electron volt. So if you add what you are getting 4.9 electron volt. Okay, and you need to calculate the work function difference. Okay, Q into phi m minus Q into phi s. Q into phi m already given, that is nothing but 4.1 electron volt. 4.1 electron volt minus 4.9. Okay, you need to calculate, you need to take as positive only, that is modulus. Let us take work function difference as a modulus. Okay, so modulus means when you are getting positive value, negative value, you need to take as positive only. And built-in potential is nothing but phi m minus phi s. Okay, so this is phi m is how much? Phi m minus phi s equal to 0.8. Okay, phi m minus phi s equal to 0.8, and flat band voltage is also equal to phi m minus phi s, that is 0.8 electron, 0.1 volts. Okay, so built-in potential is phi m minus phi s. He is asking built-in potential. This is 0.8 electron volt, and flat band voltage is 0.8 electron, 0.18 volts. Okay, so this is about the simple problem related to this. Okay, is it fine now? This problem is fine now. Shall I move forward?
Yes, sir.
Okay. Next you see mass under external bias. Okay. So basically, I told you. So MOS capacitor. So MOS capacitor means it consists of what previously I told. So this MOS capacitor. So it have gate terminal and body. So body we are connecting with the ground only. So this how much of this gate voltage we are applying, that will decide. Okay, basically body is connected to ground only, but we are connecting this gate. Okay, depends on this region of operation. Okay, based on the gate voltage only, it will decide in which region this is operating. Okay, this is gate terminal. Okay, so here if you see, so here if you see, here we apply external bias. We apply external bias to MOS by gate voltage VG and substrate voltage what VB. Okay. Here we keep what VB constant. I told you, no, VB is connected to ground. So we are keeping VB. The substrate voltage equal to what? 0. So that is constant only. So which one is controlling? So gate voltage is controlling. So that means here gate voltage is a controlling voltage. Gate voltage is the controlling voltage. Okay, so depending on the polarity and magnitude of VG. Okay, so depending on the polarity, so polarity means for VG you can apply negative voltage, or for VG you can apply positive voltage. Depending on this polarity, this gate will be operated in different types of regions. Okay, and magnitude also. Magnitude means what? Value. Magnitude means what? Value. So depending on this, it will be operated in three regions. Okay, three different regions. What are those? Accumulation region, depletion region, and inversion region. Okay, accumulation, depletion, and inversion. Okay, so we'll discuss all these three regions in detail. Okay, so if you see, so accumulation means here when Vg is less than zero, when Vg is less than zero and Vb equal to zero, what happens? Here you are applying Vg less than zero means you are applying negative voltage. Okay, you are applying negative voltage. So what happens here? What are the majority carriers in p-type substrate? P-type substrate. What are the majority carriers? Holes. Okay.
Volts.
So due to this negative voltage, what happens here? SiO2 layer is already there. So some more holes will be attracted toward this negative charge, and thus will be accumulated on the surface of the substrate. Surface of the oxide, we can say the surface of the oxide. Okay, so here what happens here, carrier concentration becomes larger on the surface. Here this carrier, what are the carrier concentrations? What are carriers here? Holes. What are carriers? Holes. Okay, holes will accumulate. Okay, holes will be added due to this negative charge. Okay, and this will be available due to this. This is a insulator. It will not pass through. Okay, so it will be accumulated on the surface of this. We can surface of the we can call a substrate or surface of the below oxide layer. Okay, accumulated below oxide layer. Below oxide layer. Okay, so this is called, we call as accumulation of carriers on the surface. So accumulation means what? I told you, accumulation means adding. Accumulation is nothing but adding. Okay, or we can call as increasing. Okay, adding, accumulation, adding. Okay, so here electron concentration will go deeper inside due to negative potential. So here, what are the minority carriers in the p-type substrate? Electrons. Okay, so due to negative charge, both electrons, like poles will repel. No, so this is having negative charge and this is having negative charge. So both will repel. Okay, and both will repel. Some electrons will recombine. So whatever the electron concentration is there, that will go deeper inside. That will go deeper inside due to negative potential. Negative potential. Okay. So coming to this energy band diagram. So this is Q into Vg metal. Okay. So what happens here? Accumulation of holes are happening. So initially, when you added this energy band diagram, how it will look like? We already seen, no? So this is nothing but it will look like this. Okay. So it will look like this. Okay, one second. So it will look like this. Okay, so that means here we are adding both energy levels for metal oxide and semiconductor, and Fermi level lies in the same constant. So here it will be like in the oxide layer, that is a ramp, a ramp linearly increasing, and here you are getting some curve, and it is you are getting above this. Okay, if you see in the accumulation region, what happens, whatever that increase in ramp in the oxide layer, what happens, it will be decreased. How much it will be decreased means Q into VOX it will decrease. Okay, and after that this conduction band also. Okay, like this you will get intrinsic semiconductor, like this you will get. Okay, so this is about the accumulation. Okay, accumulation. So when you will get the accumulation, when you are applying Vg is less than 0. Okay, Vg is less than 0, you are getting accumulation. Okay, negative voltage. When you are applying Vg, when you are applying Vg as what? Negative voltage. Negative voltage. Okay, so this is about accumulation, and this is about the accumulation, MOS capacitor under accumulation. Okay, so here whatever the holes are there, that will be accumulated on the surface of the substrate. Anyway, metals means electrons only. We are applying negative voltage to the gate. Okay. So when you are applying this these holes will be accumulated. Okay. It will not pass through this. Why? Because due to this insulator, this will not pass through this. Okay. So this is we can call as charge density. Charge density. Okay. And this is electric field, and this is built-in potential. Okay. So charge density. This is the charge density. You'll get like this. You'll get the charge density. Okay. So if you integrate this rho v by epsilon, that curve will be converted into a square wave like this. Okay. And again, if you integrate this exponential, this square wave, you already seen now. When you integrate this square wave, it will be converted into ramp, and like this function will be. Okay. So this is about the different charge density, electric field, and potential with respect to this MOS capacitor under accumulation. Okay. And this is the condition 2. Condition 2 is nothing but we are applying Vg greater than 0 and small value. Okay. We are applying positive voltage, that too, which value you are applying? Small value. Okay. Small value. So when small value you are applying, what happens? So here carrier concentration, holes will move deeply. So here positive. Positive means what are the majority carriers? Holes. Okay. Holes will be repelled or attracted. So here positive. Like charges repel. So the holes will be repelled. Holes will be repelled. Okay. So when holes will be repelled, so whatever the carrier concentration, that is holes are there, that move deeply inside the p-type material, and that form a depletion region near the surface of substrate. So depletion region is due to what? Due to this negative ions. Basically, like there will be a depletion layer. So before applying positive voltage, here what happens? Holes will be there. Okay, these holes will be there. And after applying this positive voltage, what happens? These holes. So these holes are there. No. So these holes will be repelled. These holes will be repelled. Okay, these holes will be repelled and leaving the immobile ions. Immobile, immobile negative ions. Due to this immobile negative ions, there is a depletion layer formed in between where to where, between the silicon dioxide and the p-type substrate. Okay, so this is nothing but what? A depletion layer. Okay, so depletion layer is formed between the silicon substrate, p-type substrate, and a SiO2 layer. So this is the depletion layer. Depletion layer. So this is the condition 2. So what is condition 2? You are applying Vg greater than 0 and small value. Okay, and Vb is always 0 only. We are connecting this one is to ground only. So which one you are wearing means you are wearing this one. Vg you are wearing. Okay, Vg you are wearing. So here if you see, so that means depletion layer is formed. So this is Q into Vg. So here you will get like this ramp linearly increasing. Okay, and this is so semiconductor wise, if you see the like more electrons are there, so that means conduction band will be down like this. Okay, so intrinsic semiconductors also, and intrinsic Fermi level and valence band also it becomes down. Okay, so this is the energy band diagram of what? MOS. Okay, MOS when Vg is greater than 0 and small value. Small value. Okay, and next you will see. So same thing, like if you want to calculate E, so rho V by epsilon, this is the definitions and electric field you need to remember. That's why we call it depletion mode. Okay, this is depletion. Why it is depletion mode? A depletion layer is forming in this condition too. Okay, that's why we call as depletion mode. Okay, depletion mode. Okay. Next, if you see inversion layer. Okay, inversion layer means what? we are increasing more and more VGS. We are increasing more and more VGS. That means VG, that is larger value. Okay, larger value, larger positive value. So what happens here? What are the minority carriers? So minority carriers will be attracted towards you applied larger voltage. No, so due to this large and positive voltage, what happens? This will overcome this depletion layer, and this will be available on the surface of the substrate. That we call as what? Inversion. Inversion layer. I told you, no, same like that. So here p-type substrate. What are the majority carriers? Holes are the majority carriers. But in the p-type substrate, n-type material is forming. N-type material is forming. That we call as what? Inversion. Okay. So here VB is anyway 0. So why we call as inversion? For large gate values, if we increase more and more gate values, electrons will make a layer at the surface of the substrate. This is nothing but this one. This is nothing but electron is making a layer. Okay, electrons are making a layer on the surface of substrate. Okay, which is opposite to the p-type substrate. That's why we call as surface inversion. We call as surface inversion. Okay, below electron there will be a depletion layer. Okay, after some voltage, what happens? Depletion layer will not increase and electrons will increase. So depletion layer will be constant only as they increase. More and more VG voltage, okay, as they increase more and more VG voltage, what happens to depletion layer? Depletion layer will be constant only, but amount of accumulation of electrons in the surface of substrate will increase. Okay. So this is the inversion layer. This is MOS cap under inversion. Okay. This is about the MOS capacitor. Okay.